let's keep going. So let me just back up. This is showing the different stages. When we look in detail, we can see that the stages of ignition, there's actually multiple stages. Here, turn on the laser pointer. So in this first part with the A, you can see that both the HO2 and the OH are climbing together, and they both have this straight line on the log plot, which is because they're following a single exponential. And they're basically, the radical concentration is just expanding according to the explosive mode, the mode that has a positive eigenvalue. When we get to the end of stage 1A, we've reached the point where the R plus O2 reactions become equilibrated. So R plus O2 no longer makes peroxyl radicals, but instead the R plus O2 can only make HO2 plus alkene. The HO2 is much less reactive, and the corresponding eigenvalue of expansion due to the HO2 reactions is much less. So the slope drops, and also the OH and the HO2 are no longer locked together, and the HO2 they separate from each other at the time when you have this transition. Then they both propagate along, but this process is not a straight line on the log plot, and that's because as the reaction proceeds, HO2 is accumulating, and the HO2 concentration is getting high enough that you're getting second-order reactions. Maybe I should emphasize that the HO2 concentration here is multiplied by 10 to the minus 5. So it's actually like 100,000 times higher than the concentration of OH. And the second-order reactions of HO2 become significant. And that gets worse and worse until eventually the second-order reactions become dominant right here at the end of stage 1. At that point, you really no longer have amplification because the HO2 is just reacting with HO2, and there's no longer much HO2 plus RH to amplify the total number of radicals. And typically what happens then is that you see that temperature goes up because you've reached kind of like a peak of the HO2 and OH concentrations, and you see a little kink in the temperature. But you also see some goofball behavior of all the radicals as you're kind of falling off the bandwagon. You were all going along doing something, and all of a sudden that no longer works. But by the time you get to this point, you've also accumulated quite a lot of radicals. You have pretty high concentrations, and you have a lot of H2O2. And the radicals keep on driving exothermic processes, so the temperature keeps rising all through this period, and eventually gets to a temperature where the H2O2 starts to break down and makes a lot of OH. So you see the OH concentration suddenly kinks up when the H2O2 starts to break down. And that burst of OH, it reacts with fuel, it releases a lot of heat, and suddenly you get the real explosion where the temperature gets so high that the H plus O2 chain branching can take over. And so that's the normal, what we call the ignition delay. This time here, when we see the little kink in temperature, is called the first stage ignition delay, or the cool flame region sometimes. And you can measure this because you can see the T change, and some people can also measure the radicals, but that's more difficult. Usually this is not measured because the radical concentrations are so tiny. You see 10 to minus 14, really, really small back there. Super fast exponential rise. Then you see some slower thing that's not quite so clear what's happening, where the HO2 and OH are forming slowly. And then you get this kink, and this kink happens when, go back. The kink is happening when the H2O2 concentration gets so high that the self-reaction starts to be important. So initially at low HO2 concentrations, the second-order reaction is negligible. So it only can react with the fuel, because you have a lot of fuel, you have a little tiny bit of radicals. They only go this way initially. But then as this goes, you build the radical concentrations higher, 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 eventually to the point where this reaction becomes competitive with this reaction. And when that happens, you get the kink here. where everything changes because you're turning off the amplifier of HO2 plus RH, because now it's mostly just going around the blue circle around the outside, which is just linearly consuming their fuel and making heat, but it's not changing the number of radicals. So the whole thing is kind of not that dramatic. When a log plot, it looks flat. It's still rising, but it's not that much. But that's still releasing heat, and so the temperature is rising, and eventually the temperature gets to the point where the H2O2 that's building up just decomposes to make radicals. And that can happen pretty fast. And you get a sudden burst of like OH radicals being released, and then that's often enough to make it just go explode and make the ignition. Anyway, in the stage 1A, this first part, you can just calculate what the eigenvalue is, and it depends on 10 rate coefficients, but we actually have the algebraic expressions. You can do the pseudo first order analysis and analyze it and say, oh, there's these 10 rate coefficients that come in, and they're the only things that matter for the time constant of that rise. And the HO2 is pretty important then, but then later on it's less important. And mostly what's happening is just the OH is attacking stuff. So initially you have only a tiny amount of OH, but by the end of that exponential rise, you have enough OH that it starts to be pretty important. And you have the OH is eating up stuff pretty fast. And then in stage 1B, you've lost the R plus O2 channel because you've reached the point where R plus O2 is equilibrated with the product RO2. And so that doesn't work anymore. And now you're all about HO2, and as the HO2 builds up, eventually this HO2 plus HO2 reaction starts to win over the HO2 plus fuel reaction, and that reduces that. You get like increasing losses to this channel, which is like not making any amplification for you. Yeah, so this makes a point of inflection in the temperature. And you can do it. Anyway, we did the algebraic analysis. You should read the paper to get all the equations about how it goes. And then you can also then from that eigenvalue analysis get formulas for what the first stage ignition is, which is the ignition until that kink in the temperature occurs. And that's what this plot is here. And this you can measure experimentally as well. And if you just assume that you have exponential rise, you would get straight lines in these log plots. And you don't get quite a straight line, but it's pretty straight. And so that's why this simple analysis works pretty well. The temperature matters a lot. So in the calculations we did, we assumed that there's no heat losses, perfectly adiabatic. But really, in real systems, you're always losing some heat, and it can matter a lot. And you can get the whole difference between igniting and not igniting, depending on exactly what your heat losses are. And you've just seen this experimentally, right? If you try to like light a fire in a wind, you can't light it, right? So the heat losses really matter quite a lot. And then also the things that cause heat gain, temperature rise, matter a lot. So for example, if your fuel breaks up and makes a lot of formaldehyde, that really helps the ignition happen because OH plus formaldehyde is really fast and it's really exothermic. And so you get a lot of extra heat release if your fuel, the way it decomposes, makes a lot of formaldehyde. Some fuels make a lot, some make less. And so that's like a pretty important thing for the ignition. And here's like showing how different your concentrations of radicals would be if you had isothermal versus adiabatic where you just change the rate coefficient for this one reaction by a factor of 4. And you can see they're all different. So it's pretty sensitive to this stuff. And then we can get the simple formula to get the ignition delays. And so the dashed lines are the very simplistic formula, only depends on a couple of rate coefficients. The solid lines are full models with like 1,000 reactions. And you can see it's pretty close. Oh, yeah, thank you. Yeah. So all these dashed lines are the simplistic model, only depends on a couple of rate coefficients. They're the most important ones. And these solid lines are the full detailed models with about 1,000 reactions. And these for a whole bunch of different fuels, propane, butane, pentane, heptane. And you can see like basically this whole low temperature branch is essentially, it's the simplistic thing, it explains it really well. Now some fuels cannot make the species QOOH. If they're too small, they can't do the cyclic reaction where they reach back and bite their tail because there is no H there, or the ring would be too strained. And so things like methane and C2 molecules can't do it. If you have an aromatic without a side chain, it can't do it. Some small alcohols can't do it, like methanol, but they can do a different reaction. So methanol, for example, does a reaction where it extracts the H from this guy, and this guy reacts with oxygen to form HO2 plus formaldehyde. All right, so I showed you this already. The H2O2 amplifier is way less effective, has a much longer time constant than the QOH amplifier. And so it makes the temperatures longer. And so what happens is methanol mostly just does this one pathway. Propane does this pathway first and then that pathway. And you get kind of similar behavior with methanol at 800 Kelvin compared to a propane at 750 Kelvin. So changing the fuel pretty much, going from propane to methanol is a pretty big change in the fuel. It does change things, but it's only 50 Kelvin. So it's like, it depends what you care about, and whether a 50 Kelvin change in the ignition delay matters to you or not. But it would definitely be a different octane number for sure. And you can get quite good matches between the simplistic models based on the eigenvalues compared to full detailed models, as shown here. That I think the black dots are the real full model solutions, and these simple curves are just what you get from the simple eigenvalue analyses. All right. So if you want to do this for a complicated fuel, you have to compute all the hydroperoxide isomers that you can form from the fuel. And you can compute them with like RMG or Kinbot and do quantum calculations. And this is okay. It's when the molecules gets too big, this gets to be very painful. But for the smaller ones like pentanes and stuff, this is fine. And ideally, you find some way to lump these QOHs together because you have quite a lot of them. And it would be a pain in the neck to try to figure out the eigenvalue analysis with too many different similar reactions. It should be possible to do this, but I don't think anybody's ever really demonstrated how well this can work. But I think that would be an interesting thing to try. And this lumping idea might work even if you don't know the full fuel composition. So if you had a real jet fuel or a real diesel fuel, you couldn't model every single molecule because there's too many molecules. But maybe you take a few representative ones, it might be enough to get the idea. I want to emphasize that the complexity of this is not like I'm making this up. The fuels are super complicated. They have so many different isomers and so many different proxy radicals you can form. And so if you wanted to try to really get this in every detail, you're going to have a very, very complicated models. And for the light fuels, we're okay. So I think there's like a pretty good prospect that by next year, maybe we have all the molecules in gasoline under control. But as you get to bigger molecules, so gasoline's up to about 8 carbons. If you go up to 10 carbons or 12 carbons or 15 carbons, the problem gets much worse because the combinatorics of all the different reactive sites and all the different molecules, it makes it much worse. And so I don't think that's practical. So I think gasoline is possible, maybe jet fuel. Diesel, no way. So if we really, if it turns out that we need to know everything about all the fuels, we're never going to know it all. So the key question is like, what simplifications can we get away with? And here's just a picture to show how these two cycles are coupled together. It's kind of helpful to understand that these yellow spots are the key, is like the branching points where two different things can happen. And knowing those competitions is like very, very important. But it's only a few. It's only a few of them. So if you know this, this rate versus that rate, or this rate versus that rate, that's like very crucial information that's specific to the fuel. But it's not like an infinite amount of information you need to know about each fuel. So I think it's kind of possible. There's like 5 key branch points in the chemistry. What matters the most is this first thing of like, how can you get this cycle going? How far does it go? And then the second one is a little simpler because it's a simpler little cycle, right? It's just RO2 falling apart to HO2. And so this one is maybe not so bad to do. But you need HO2 attacking all of the hydrogens in the fuel, because it'll find the weakest hydrogen in the mixture will be the one that gets attacked by the HO2. And so that's quite important. And we see that when you add additives, if you add additives that have weak OH bonds, for example, they really have a gigantic effect on the octane number, because they can really divert the chemistry a lot, because the HO2 is very selective. So OH radicals are super reactive. They react with everything. But HO2 radicals are super unreactive, and they're therefore very selective to go only for the few reactions that they can do that are not too endothermic. They'll be basically the only reactions you see. So in your fuel, if most of your fuel won't react with HO2 and you put a little bit of additive in that can, you can really dramatically affect the ignition delay of the fuel. All right. So the summary. If you focus on the important physics in each stage, you can really simplify and understand even very, very complicated systems. And you can do an eigenvalue analysis and then get a simple analytical formula, and at least parts of the chemistry, you can just predict it just perfectly without knowing many rate coefficients at all. You can do similar analyses for systems where the hydrogen peroxide amplifier is controlling, but this gets more complicated because things like the heat release from the other side reactions are really important because it's very sensitive to the temperature. But overall, the ignition is controlled by some tens of reactions, not by hundreds or thousands. So it's like believable that this might be computable. And a key question is like, can we calculate them accurately enough? Can we measure them? How do we best combine the theory and experiment? I think this is like a challenge for the community of how to do it properly. And I just want to acknowledge this whole analysis with the eigenvalues is mostly done by my student, Shamal Merchant, who's now long gone, but when he was a student for me. And these guys all worked on the alcohol problem, including Meni Sarathi from KAUST. And there was a lot of previous work on this, particularly by Norbert Peters. And then recently, Tianfeng Liu and Ed Law have done a nice analysis. And actually, Ed Law is still working in this area and did some really nice papers recently about this. All right, so that's that. All right, so we did soot, we did ignition. Now let's look at fuel requirements. Right. All right, so what do we need in a fuel? Maybe I'll back up. Why do we care about this? So we started at the very beginning. We said, we have a problem because all our transportation fuels are coming from petroleum. That's a fossil fuel. That's making CO2 go in the atmosphere. The fuels that we use to make electricity are coal and natural gas mostly, and also to make industrial heat and heat our buildings. And those are also making a lot of carbon dioxide go in the air. So we have to figure out what to do. For the electricity, we have the idea that we could do nuclear power, hydropower, solar power, wind power. and maybe we can get enough electricity. So maybe electricity is not the main challenge, at least not in the US, not in a lot of countries. Some countries don't have the resources, have some problem with nuclear power. Maybe they still have a problem. But a lot of countries, we know how to make electricity in a way that's not too much carbon emitting, and so we could do it, and more a question of like, who's going to pay, how fast can we make the investments, what's the permits, stuff like that. For the transportation and the heat, we don't know what to do, fundamentally. And so for some subfields, there's agreement. So for example, in aviation, people think we're definitely going to make the jet fuel out of biomass. That's like the consensus view, for sure, of Boeing and Airbus. And since they make all the airplanes, they're the ones that matter. So that's probably what's going to happen. And people who are rich enough to fly by airplane are willing to pay a little bit more for tickets. And so you can raise the price and use a more expensive fuel made from biomass. It seems like very believable that you could do that. In other parts, like trucks or ships, it's really not so clear what we're going to do. And for industrial heat, it's really very unclear. And so even in the jet fuel case, they're going to try to make a jet fuel out of biomass that's the same as petroleum jet fuel, but it will not be the same because it's not the same starting material. So there's an issue there. We're going to have a new fuel for airplanes soon, maybe several, as people work out like what to do with biomass and which biomass to start with. They're all different. So you're going to get a lot of mixtures of stuff. Then when we go to the other ones, we don't even know what we're doing. So we're going to have to try new fuels, maybe try new engines, iterate back and forth a few times. And so potentially we might need quite a few fuel models to understand it. And it's very good to like try to narrow in what do we really care about. If we're like going to change the fuel, what are we going to do? So we as we talked in the very first slide, presentation. You need a high energy density. This is really crucial. Mostly we want stuff that reacts with O2 to help with the energy density. And usually want it to be really hot because then you get high power density, high burn rate, actually high efficiency in heat engines. So usually this is like how we would want to do it. So you'd really want to have this high energy like this. And then you can't afford for the fuel to be toxic, the products to be toxic, because otherwise when you have a spill, it's going to be a disaster. And very importantly, people are cheap. They don't want to spend a lot of money on fuel. So you need affordable price, and you need a gigantic quantity because there's a lot of people, and we all want fuel. So if they're all going to get enough fuel, you need a lot of it. So we need something like 10 million tons per day and price less than $20 per gigajoule. That would be really great. Then we would be happy. The price matters. So for example, this shows the oil price versus time. And the gray bars are times when there were recessions. And what you can see is that they're not 100% correlated. Like here's a bunch of recessions happening that had nothing to do with oil. But here's one, here's one, here's one, So there definitely seems like there's some correlation. When the oil price gets really high, we have a recession in the world. And there's also been other problems. There were a couple times there were blockades or embargoes and other kinds of supply disruptions, many of them related to wars, and they caused a lot of trouble. And also, in different countries and different times, the fuel taxes and the fuel policies change pretty wildly, depending on the opinion of the government of the day. And so that can also cause wild effects on the price to the consumer in these countries. And that can affect the economy also and affect the consumer behavior. All right, so from that plot, just a quiz for you. The oil price started rising dramatically starting about 2000, and it remained very high up to about 2012. So you can see here, 2000, it went from like $30 a barrel up to $160 a barrel, factor of 5 increase in price. And the gasoline consumption has been dropping in the USA and Western Europe. And the oil production has risen. And all through this period, the oil price was much higher than the cost of producing the oil. Why do you think the price went up so much, even though the oil production was increasing very significantly during that time? You guys remember from economics, right? You think normally when the production of something goes up, you would think the price would go down. But in this case, the production went up and the price went up. What's going on? I say it again? Consumption was going high, okay. But in US and Western Europe, it was not going high. So where was it going up? Yeah? Exactly. That's right. So especially China, during that period, early 2000s, the Chinese economy was growing from pretty small to really gigantic during that time. And so the oil consumption, and actually consumption of a lot of commodities, went up like crazy, even though in some of the more well-established economies, nothing special was happening. The overall consumption was going up, and it went up even faster than the production. And in fact, you could argue the other way, that the production went up because the price was going up. Down here, when the price was really low, nobody was inspired to spend much effort on production. But once the price got up to here to $80, $90, $100 a barrel, then the producers say, wow, I can make a lot of money if I produce. And so people worked really hard to increase the production. Did you have something to say over there? No. Right. So anyway, this illustrates that fuel price fluctuations can be a big problem. And it adds a lot of risk to the alternative fuel projects. So like in the 1980s in the United States, there was a lot of effort, late 70s and early 80s, to try to get away from petroleum, because the United States had suffered from the oil embargo in 1974, I think. And there were like gas lines, and people couldn't get gas for their cars. And so people were like, we really need to make alternative fuels. So a whole ton of companies started to try to make alternative fuels, and the government gave them a lot of money, and they all started making fuels, and then they all went bankrupt. So if you can see what happened, the price went really high. They all worked super hard to make alternative fuels, but the price went down. And then all the investors who invested in all those alternative fuel companies went bankrupt because oil was so cheap that nothing that they could make as an alternative fuel could compete, and stayed down for a long time, so they all went bust. So it's a problem for the economy if the oil price gets high, but it's actually a problem for the alternative fuel production if the price gets too low. If the oil price gets low, then it undercuts all the other alternatives, and it can wipe them out. The price fluctuations are often larger than the technological or political uncertainties. And so this is like the biggest investment risk when you're trying to decide whether to invest in an alternative fuel, is how confident you are you can predict the future price. Because if the future price is high, you're going to make money. And if the future price is low, you're going to be bankrupt and lose your whole investment. And so you have to be pretty confident that it's going to stay high and not be low, unless you have a rich uncle who's going to bail you out or something. And there's a definite possibility that the producers might intentionally try to drop the oil price to try to drive the competitors into bankruptcy. And there's some evidence that this has happened at times in the past. When OPEC decided the other guys are getting too competitive, they just dropped the price in general, and they could make the price lower and still operate. And a lot of the other alternative competitors could not, and would drive them into bankruptcy. And then because of this whole thing, it makes the whole investment super risky. And because of that, then the only people who invest are people who are gamblers. And they want to make like a gigantic return because they know they're risking a lot. So they don't want just a 5% return. They want like 30% return, 50% return, because they're worried that the price is not going to stay high very long. They better get their money back quick before the new business goes bankrupt. And so this is a problem because the less lucrative processes are never built. And so that's really slowed development of alternative fuels. And we went through and we talked about the properties. You don't want to have solids. You like liquids the best. You need to be able to control the emissions to make sure you're not going to kill people or make them sick. It's easiest if your fuel will evaporate nicely so you can burn it easily. And you definitely want to make sure you don't have big greenhouse gas emissions. In practice, the emission requirements are very controlling. So for example, in the gasoline engines, the fuel-to-air ratio today is always held near stoichiometric. The reason for that is that they want to use the three-way catalyst, and that catalyst only operates well near stoichiometric. So you have to operate near stoichiometric because you need to use that catalyst because it's the only way you can meet the emission requirements. And to suggest that maybe you could even run combustion ignition engines that way if you wanted to. If you don't have a three-way catalyst, it's really difficult to meet the NOx standards. And so, for example, in the United States right now, many people are trying to change the gas burners in furnaces with special low NOx burners, but it's pretty difficult to get very low NOx. So for example, in Houston, there's a very big chemical industry there that you have lots and lots of boilers and furnaces. And they really need to go back and retrofit every single one of them to be a low NOx burner. And you have to figure out how can you make your low NOx burner so good that you can get down to the regulated NOx emissions. And they need to do it there because there's so many of them close together, they really affect the smog in the Houston area and makes it very unhealthy for people on some of the days because of all the NOx emissions. The diesel engines have to operate either at some very special low temperature conditions to try to reduce the NOx emissions, or they have to do a special emission control. Typically they use a urea and a catalyst reacting in the tailpipe to try to reduce the NOx. And then you also have to use a soot filter. So diesel engines right now, modern ones, are really complicated emission controls, many thousands of dollars, emission control equipment on the trucks. This was a headache for the diesel manufacturers, and there was a pretty famous scandal. I don't know if you guys are old enough to remember it. Do you guys remember the scandal? There's a bunch of the German diesel manufacturers cheated the NOx test, and they got caught. It was like a huge embarrassment. And they basically cheated because they wanted to comply to meet the government requirement, but then they couldn't really make the diesel engine work that well when they were running that way. So they were like, well, it'd be easier just to not really meet the requirement. Actually, just recently, last week, there was a similar kind of scandal in Japan with several of the Japanese engine manufacturers cheating on the test there. So it's like it just emphasizes that if you're going to have a regulation, you have to have a very good regime to keep enforcing it. Otherwise, eventually, people will be tempted to cheat and not comply with it anymore. All right, another quiz question. So diesel engines cost more. They have more complicated emission controls. They're more expensive to manufacture. But nonetheless, a lot of people in Europe buy diesel engines. Why do they buy diesel vehicles, like diesel cars? Why do Europeans buy diesel cars, but Americans don't buy diesel cars very much? Any ideas? Or what?
No, sorry, I read this.
Okay. Anybody else? Why do you think people? Yeah.
No. What did he say?
He said he withdrew his question. Withdrew his answer. Sorry. So the question is, why do a lot of people in Europe buy diesel cars? Almost nobody in America buys a diesel car. Why is this? Yeah.
It's very, at least in the Netherlands, if you drive over 50,000 kilometers a year, diesel is way cheaper because the fuel is way cheaper and you pay more taxes. So there's like a great diesel price.
Okay, so for people in the Netherlands, she said if people in the Netherlands, when they drive, if they think they're going to drive more than some amount of kilometers per year, they can calculate that it will save them money to use a diesel instead because the diesel fuel is cheaper.
And you pay more taxes.
On what? On gasoline or diesel?
No, on road taxes.
On more road taxes in diesel or gasoline.
Diesel.
But then,
So diesel's cheap, but you pay a fixed amount per 3 months, per year, extra in terms of taxes.
okay. Okay, and then somehow it works out that you drive enough miles, the diesel is better. And for gasoline, it's more. Now, it's interesting, in this country, do you guys know the diesel versus gasoline price? Anybody?
Diesel's way more expensive.
Yeah, so diesel's almost $5 a gallon here, and gasoline's only like $3.50. So it's like a way cheaper for gasoline here. So why would that be? Why would the price for diesel and gasoline be different at different sides of the ocean?
Sources.
Refinery plants in there.
It could be, could be like that somehow it's cheaper to produce it. But you think it was such a big difference, maybe just people would put it in a boat and ship it across, right, to balance.
And
So,
also the tax are lower on
the tax.
so there has been governmentally incentive.
Yeah, so the gasoline in Europe is way more expensive than in the US, right?
Both from there.
It's not the production cost. So what's the difference?
Pipelines?
No,
Taxes.
taxes, all taxes. Yeah. So the taxes, so what happened in this country after the Arab oil embargo in 1974, the US all tried to make alternative fuels. It didn't work. All the business went bankrupt. And then the oil price dropped and we forgot about it. In Europe, when they had the same experience, they said, oh man, we don't want this to happen again. We're going to try to reduce our dependency on importing petroleum. And so they said, how can we do that? They said, let's raise the taxes on gasoline. And many countries in Europe agreed to do it and have stuck with it since the 1970s. So oftentimes the price in gasoline in Europe is double the price of gasoline in this country, and that whole chunk is just tax, pretty much. And so therefore, from the consumer behavior, people will change to try to avoid the high tax. So one way is people use more efficient cars in Europe, so they have higher fuel economy. And the other one is you just say, oh, I'm not going to use gasoline at all, get the diesel because it's not as taxed as much. And that's interesting politics that somehow the government decided to not tax the diesel so much, but just to tax the gasoline. Yeah, so the truck, maybe they didn't want to get in trouble with the truckers, or what, yeah. That's very, I don't know the history of that. Right, so yeah, so I don't know how that historically, how that happened and what the government was thinking, but anyway, that's what they did. And that also set up the pricing incentives for the refineries. So the refineries then, their product was taxed less if it was more diesel, so they adjusted the refineries to make them make more diesel. Yeah, so that's cool, and that amplified the effect. All right. So different engines need different fuel performance properties, and very importantly is the ignition delays, which we talked about last time. For the auto engines, you always want long ignition delays. The higher the octane number, the better. You really don't want any spontaneous ignition. You only want ignition due to the spark. And then you need low temperature evaporation because you want to make a perfect fuel-air mixture, and so you have to have all the droplets evaporate in the time scale that the piston's going up and down. And then also you need a sufficient flame speed, so you can burn all the fuel between the times that the piston moves. The diesel and jet, you typically want easy ignition, so once you squirt the fuel in, you have a fire. And you want good enough evaporation so that the liquid's evaporated before the droplets can go all the way across the piston. So that sort of sets the minimum amount of evaporation you can have. And then you really like it if it was resistant to soot formation. Yeah, and so fuel rich versus fuel lean is kind of simple. If the system's fuel lean, at equilibrium, the carbon will be in form of CO2. If the system is fuel rich, even if we consume all the O2, we're still going to have some CO or hydrogen or onboard fuel left over. But it turns out that if the O to C ratio is greater than 1:1, we normally won't make soot. We'll just make CO. But if it's O to C is less than 1:1, that means we don't have enough oxygen to bind every carbon atom. we're going to have some carbons left over, and they're very likely to make soot. And that's the problem. And so these are the primary air pollutants that people are worried about due to health mostly, and then this one for greenhouse effect. And then all the primary sources. And many of them are from engines and vehicles. Some of them are from electricity production from fossil fuels or industrial boilers. And these are all the reasons why we don't like any of these pollutants here. Probably you guys know most of these, but this is important to know. Back in 2001, we had various bad acid rain in this country, due primarily to burning coal with a lot of sulfur in it. And then they made very strict regulations on the coal power plants, requiring them to remove the sulfur, the SO2 coming out of the smokestacks. And since then, the acid rain problem is much reduced. But we still have NOx is still a pretty big problem, and a lot of the smog problems we have are related to NOx formation. And then, of course, the CO2. So you can see that the atmospheric concentrations are going up, 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 up. And we know how much emissions we made. And you can see basically we're emitting very, very fast now. And these are a plot of as of COP21, what the projections were. At that time, the policies would have led to a very hot world of about 3-degree rise in global temperatures. Nowadays, we're more or less on this yellow track, maybe somewhere between 2 and 3 degrees. And the Paris Agreement is we're all supposed to try to get the number below 2 degrees. So we have, but right now we are not on that track. So we're more or less on this yellow track here. So that's the challenge for you guys. And I think we'll take a break now and come back at 4:30 to discuss NOx chemistry.